Well, thank you everybody for coming. I am very happy to have the opportunity to talk to you a little bit about operations and the aerobraking maneuver that we finished earlier this year. As Tom mentioned, my name is Theiling. I am the lead for the Science Operations Center here at LASP. Short version about what we do: we basically design and build the observations that the scientists want and provide those to the MSA down at Lockheed Martin to effectively communicate to the spacecraft what it is the scientists are looking to get out of it. And then on the downlink side, we do some of the initial processing of that data and then disseminate it out to the various science groups. So a little bit about what I'm going to talk about. I'm going to give you a very brief history of MAVEN. If any of you have been to previous presentations, you may know some of that already, but I'll keep it quick. I'm going to talk a little bit about the general science operations that we had been doing up until January of this year. And then I'm going to talk a little bit about what relay operations entail and sort of a comparison between the two. And then I'll actually get to the topic of aerobraking. And then I'll tell a little bit about the science impacts and what has occurred, what has had to change because of our change for aerobraking. And then a little bit about what's coming up after that. So, brief history of MAVEN. MAVEN stands for, it is an acronym, it stands for the Mars Atmospheric and Volatile Evolution Mission. We launched on November 18th of 2013 and arrived at Mars on September 22nd of 2014 with Mars orbit insertion. Interesting side note, you may remember as soon as we got to Mars, a comet also arrived very close to Mars. And they're very dirty, spewing lots of gas and dust all over the place. And so the only sane thing that a brand new satellite with brand new instruments that hadn't been fully checked out in orbit around Mars, the only sane thing that we could do was turn all of our instruments to that and start taking pictures like crazy. So we did that even before we had fully checked out the spacecraft and took some invaluable science about how comets interact with the Martian atmosphere. And a lot was learned about that. So soon after that, in November of 2014, we started taking data. It started out pretty simple, but as we went along, it got better and better and more complicated until we get to the present, where we're taking pretty high resolution data of many different types of the Martian upper and middle atmosphere, trying to look at how the atmosphere has evolved over the last several billion years. But enough about all that interesting science. We'll talk a little bit about operations. The orbit that MAVEN is in is fairly elliptical. We have, this is designed in such a way so that we can take observations across a wide range of altitudes and cross sections of the planet's atmosphere. The red section there towards the top right that I have the arrow pointed to is called the periapse segment. We call this because periapsis is the closest point in an orbit to the body that it's orbiting. This is the segment of the orbit where we do a lot of our what's called in situ atmospheric measurements. This is where MAVEN actually dips down into the middle or the upper atmosphere and takes measurements there. And so you can see on this plot, I don't know how well, there's my mouse, this solid dashed line right here represents the orbit of Mars. Now at the bottom you have time on the x-axis and altitude here on the y-axis. And so as time goes by, MAVEN dips lower and lower into the atmosphere. It reaches into this exobase area here and then climbs back out of it. And this is the area that we're predominantly interested in from in situ measurements, in situ being in place. Every so often, and this will be a little more important when I get a little further down the line, is there's this dashed line here that you see labeled as deep dips. These are campaigns that we do every so often. We've done 9 of them so far in our science orbit, where we purposely dip even deeper into the atmosphere to get down to this low level around 120 kilometers called the homopause. This is the middle atmosphere, middle layers of the atmosphere of Mars, and is also very good science that we can't get often because you can imagine dipping into the atmosphere has its risks. Talk more about that as we go. Yellow sections on here are the side segments of the orbit where we move in towards the planet and then on the other side climb back up to higher altitudes. This is the region where you get into more of where the interactions of the solar wind are interacting with the atmosphere of Mars and what little bit of a magnetic field is available. There are several other webinars that cover these topics. I highly recommend you take a look at them. They're very good. And so the side segment the atmosphere and look at slightly higher altitude sections of the atmosphere. The light blue segment here is the is the APOAP segment. This point is the farthest orbit. I'm getting signals that my internet connection is unstable. I'm not sure. Can you still hear me okay, Christine?
I can hear you now, but you cut out a little bit. If you want to, go ahead and you can try stopping your video. That might help temporarily anyway, while it's being unstable.
Okay, it seems like it may have corrected itself, so we'll see if we can keep going.
Okay. If you get the signal again, please just go ahead and pause your video.
Sure. I apologize for that change. So this last fourth section here is the APOAP segment. This segment is effectively out of the atmosphere, well out of the atmosphere and into the corona of Mars. But it provides an opportunity for us to turn cameras to Mars itself and get some very wonderful high-resolution images of the full disk of Mars. And since we can do that in every orbit, you can see how clouds move around the planet and how changes occur from a full view of the planet. So
we've got our first question while you're working on the next section. What is the difference between all the different layers of atmosphere at Mars?
Yeah, that's a good question, and I have to admit I'm not an atmosphericist, so I can't answer that question in any great detail. But Mars has layers in the atmosphere a lot like the way Earth does. Of course, it's predominantly carbon dioxide, very little water, and virtually no oxygen whatsoever. But it works much the same way as it does on Earth, with different layers predominantly driven by temperature. Upper layers interact with the solar wind in ways that our atmosphere does not, so it's very different in that extent. But it does have a high corona and a constant process of escape, where bits and pieces of the atmosphere are constantly leaving Mars, which is what MAVEN is there to ultimately study.
Thank you.
Sure. So this is a little bit about science operations. This leads us up to where we were at the beginning of this year when we start taking on the added responsibility of doing relay. So I'll talk a little bit about relay operations and what that entails and why MAVEN is also very good at that. So let's imagine that you have your lovely little rover on Mars there. That's Curiosity waving. And you want to communicate the data you took back to Earth. Now, Curiosity can communicate directly with Earth, does it sometimes, but it's fairly slow. At about a maximum, it can handle about 32 kilobits per second. So those of us old enough to remember dial-up modems, that's the sort of level that you're talking about there. So a gigabit, which is an easily produced amount of data for a rover like Curiosity, would take 8.7 hours to reach Earth. Now let's say instead you decide that you have a lovely little orbiter in orbit around Mars that's much closer, and so Curiosity is able to communicate more effectively with that asset. Going from Curiosity to MAVEN, that bandwidth jumps up to about 2,000 kilobits per second as a maximum. And so that kilobit, or gigabit, excuse me, of data only takes 8.3 minutes to get to the spacecraft. Now, because we're partially designed for it, we can then transmit back to Earth at about half that rate, 1,000 kilobits per second. So that gigabit takes about 16.7 minutes to get back to Earth. So you can see that even if you're having to account for the time it takes for to go from the rover to MAVEN and then whatever setup time or science that we're doing and then back to Earth, you can see that it actually gets quite a bit more data back to Earth much faster to have a relay. So the reasons for this, we have a very large high gain antenna. Curiosity has one that's on the order of maybe 8 inches, 9 inches or so, something like that. MAVEN's is a little over 2 meters. You can see it quite prominently in that little image there. And so we're able to push a lot more, a larger radio signal to Earth with that. We also have more power. Those great big solar arrays make it so that we can transmit at a higher rate. And frankly, we have a longer visibility with Earth. Being in orbit allows us to have Earth within our line of sight for 16 to 18 hours out of every Martian day. For Curiosity, there's going to be half of a Martian day every day where Earth is set effectively below the horizon. And so we have more time available to transmit that data. Now, all of these things are great when it comes to relay. However, they're terrible for the science that we want to do. And also, vice versa. Relay operations and science operations don't play great together because there are differing things that you're trying to accomplish with the two of them. So let's talk a little bit about where those things sort of break down. So we go back to our little cartoon orbit here right now, and we'll sort of compare what's good for science and what's good for relay. Well, we mentioned that high altitude apoapsis. That's great for science because it allows us to get those beautiful full disk images of Mars and to be able to see how that entire surface portion of Mars is changing over time. Not so great for relay. When you can imagine at apoapsis, we're about as far from the planet and therefore as far from the ground assets as we can be. And so we don't, the bandwidth available to us is actually slightly decreased. It also turns out through orbital mechanics that when you're at the highest portion of your orbit, you're also going about as slow as you can ever go in that orbit. And so we spend the majority of our time in orbit in and around that apoapse segment. So if Curiosity happens to be on the other side of the planet, it's going to be hours before we come back around and have that overflight to be able to get the data from the rover. The low periapse altitude is also great for science. I mentioned this is an opportunity to get these in situ, in place, in the atmosphere data. That is invaluable if you're going to be talking about how that evolution of the atmosphere has occurred. Terrible for relay for two reasons. One, even though we're nice and close to the planet at that stage of the orbit, we're moving very quickly. And so if Curiosity wants to communicate data to us, it has to do it on the order of minutes in order to be able to catch us before we swing back around towards the other side of the planet. The other reason that it's bad is because we're actually dragging through the atmosphere. And dragging through the atmosphere sets up some imprecision in our ability to predict our orbit out into the future. It's a very small amount, but orbit after orbit, it does in fact build. And so if you are Curiosity or some other lander on the surface of Mars, and you want to predict out when you're going to be able to have a relay and how much data you're going to be able to return, not having a predictable relay of where it's going to be in the orbit is a pretty big downside. And so that imprecision and changeability in our orbit due to the drag of the atmosphere is bad for relay. I didn't talk too much about this, I'll mention it here. A lot of our observations that we do throughout this orbit are instrument and science driven. Each of these different segments of the orbit have a completely separate orientation, completely different pointing for the instruments, and different primary goals that we're trying to get out of the science. So MAVEN is not just in a static orbit around the planet. It is constantly changing position, rotating, tilting. The instruments are looking in all different directions. That dynamic aspect of orientation and positionability for the spacecraft is a huge boon for science because it means we can take advantage of all the different aspects of the orbit and take measurements that are best suited for where we are in our altitude and position above the planet. So, great for science. Again, not great for relay. What relay wants is for its instrumentation to be pointing down, nadir, at the planet at all times during the orbit, pretty much a set position to the spacecraft. That's not fun from a science point of view, to be frank, because we want to be able to look in lots of different places and to be able to change where we look in order to have different activities if special science it makes itself available. So what you really want for a relay is an orbit that's a little more circular, lower apoapse, higher periapse, and a more fixed position to the spacecraft. Now, there are a couple of spacecraft around Mars that are more like that. You may have heard of Mars Reconnaissance Orbiter and Odyssey, both solid science spacecraft, but also do a great amount of relay because they're closer into the planet and are better suited for relay operations. Excuse me. However, they're getting old. MRO is, I believe, 13 years old, and Odyssey is 18. So they're getting pretty long in the tooth. And that level of technology that they still have on board simply doesn't move as much data as MAVEN can with its more up-to-date technology. And so MAVEN is a very necessary part to the communications aspects that we have in orbit around Mars. And so several years ago, NASA directed the MAVEN mission to move itself, or better position itself, generally as a relay orbiter, as well as continuing doing the science that we do. One piece of that was to change our orbit to be better able to support relay operations. So how do you change the orbit of a spacecraft once you're there? Well, one way to do it is to just use thrusters. You can boost yourself into a new orbit by burning fuel. This does, in fact, take fuel, which is a non-renewable resource when you're at Mars. What you take is what you have. Now, to give a sort of comparison for this about why, and to explain why we don't want to do it this way, I'll show you a couple of examples, because MAVEN has done 2 burns like this in the past. Soon after we reached Mars and went into Mars Orbit Insertion, MOI, we actually went into a 35-hour capture orbit. And soon after that, we did a burn to get us down to a 5.5-hour transition orbit. Now, when we did this, this was called PRM1, we burned about 257 kilograms of fuel just to make that change. But we did it very quickly in the span of a single thrust, a single orbit. We did it a couple of days later to go from our 5.5-hour transition orbit to the 4.5-hour science orbit. That was much smaller, but that still used 41 kilograms of fuel. And the reason I want to point this out is because that sort of a burn from 5.5 hours to 4.5 hours is approximately what we would have had to do in order to go down to our what we call science and relay orbit. And so it's a good comparison. And so when you look at that 41 kilograms of fuel burned all at once to change the orbit, that actually translates out to about 4.5 years of nominal science and relay operations. Once we run out of fuel, we're out of it. And so we want to try and save as much of it as we can. So a better way of going about this is aerobraking. So this is a slightly exaggerated orbit for MAVEN to extend it out and sort of show you what we're looking at here. But if you imagine that far outside orbit as our original science orbit, we would then work our way down to do this. But our goal is to save as much fuel as we possibly can. Orbital dynamics says that when you do a boost out at your apoapsis point, you will change where your periapse point is in relation to the planet. So what we did is our initial aerobraking burn occurs out at the apoapsis point, and that drops the periapsis altitude into the Martian atmosphere a little bit deeper. And when you change your velocity at that point, at periapsis, by dragging into the atmosphere and slowing down the spacecraft, it changes the point at which your apoapsis occurs, the high end of your orbit. And so if you manage this orbit so that you drag through the atmosphere at just the right amount every single orbit, you will slowly step your way closer and closer to the planet. Now, this still requires a little bit of fuel, but not nearly as much as would be taken to do it in a single burn. And I'll talk a little bit more about that as well. Let's see. So what did MAVEN do specifically? Well, on the far left there, you see our orbit as it stood in January 2019. We got up to about 6,200 kilometers in our apoapsis and down to about 150 kilometers at periapsis. And our orbital period was 4.5 hours. So on February 11th, we did our first what we call walk-in burn. This is because we sort of step ourselves down into the atmosphere. It turns out it was the only think we did 2 walk-in burns to get to what we refer to as the density corridor that we want to get to. That's the level, the density of atmosphere that we want to be dragging through in order for this to work. All of this stuff is planned and calculated out well ahead of time, as you can imagine. This lowered our periapsis point down to an altitude of about 125 kilometers. And up to this point, this was nothing new. Remember, I mentioned the deep dips that we had done earlier to get that low or the middle atmospheric science. This is exactly the same thing that we had done those 9 times before in those campaigns. And so we weren't too worried about this. The new part was that whereas in the deep dips we had done this for a few days, maybe a week, we did this for 7 weeks nonstop in order to decrease our orbit. And it takes near constant monitoring of the spacecraft in order to be exactly sure that you're burning the fuel you intend to burn, that you're getting the resistance that you want to get, that your orbit is where you expect it to be, and that everything is going well. Needless to say, this heats up your spacecraft, so that has to be monitored as well. And so we had a special dispensation from NASA and the Deep Space Network to be in near continuous communication with our spacecraft, as much as that matters when you're 2 planets or a planet away, so that we could react to changes far more quickly than we usually do. We usually talk to the spacecraft twice a week. This was several times a day, luckily. And so all of this was continuously monitored. And one of the things that's sort of a miracle from my point of view for this is that all the while we're doing these maneuvers that have to be paid attention to, 5 times a day. We do about 5 orbits a day. The entire time we're continuing to do science throughout all of this, which is somewhat uncommon. A lot of other missions say, okay, science, you're done. We have to change the orbit, take a vacation, we'll get back to you. MAVEN's not usually willing to do that. We want every minute of science we can possibly get. So our orbit decreased about 12 seconds in duration every orbit. And so you can see that's not much as you go, but it steps down as it goes. And I'll talk a little bit more about that as well. And then on April 3rd, we did our last walkout burn to get into our new, what we call science and relay orbit, because we're going to be doing both of those there. Our apoapsis had dropped down to about 4,500 kilometers. Periapsis was still at 150 kilometers, but our period had decreased by an hour to about 3.5. All said and done, total fuel cost for this entire maneuver, 7 kilograms. Way less than the 41 that it would have taken to do this all at once. And so that ends up extending the MAVEN lifetime, at least from a fuel budget point of view. And after all this was done, we had ended up using less fuel than we had actually intended. And so MAVEN's fuel budget-wise lifetime has now been extended out to 2033, I believe is the case. So we have a lot of time to relay a lot of data back to Earth and to also take as much science as we possibly can. So speaking of the science, I'll talk a little bit about what the impacts were. Is there a question, Christine?
There is a question before
okay.
The science, and one is in terms of the mission itself. How large is the data buffer on MAVEN? Do you know?
That's a very good question. I can actually check a chart that I just happen to have up here. Let's see. I believe we have on the order of about 4 gigabytes, excuse me, about 4 gigabytes all said and done. And that memory is divided up. A large portion of it is used by the spacecraft itself. Each of the instruments gets a memory section. Some ancillary data gets a section, and there's also a section for relay designed for the data that we pull up from the ground assets to store there until we can send it back to Earth.
Then in terms of the aerobraking itself, I have a question in terms of whether this would be an accurate analogy to aerobraking. You know how when you're canoeing and you can change direction by holding your paddle in the water until your canoe changes versus paddling furiously to try to get it to change direction? Would that be accurate?
Yeah, I could see that as being an analogy. I'm trying to think of a good analogy on my own, and I don't know of one necessarily. But yeah, I think that does work. I think you can think of it as that way.
Thank you.
Of course. So a little bit about what we've had to do as far as modifying the science. So like I said, we kept doing science during aerobraking, which was a bit of a challenge. So let's see, here's a little cartoon designed to show you the largest circle there is our original orbit. The inner circle is where we ended up, circle I should say, ellipse. And then just the intermediary one to sort of show you that we're talking about stepping in the orbit as we go. So this is just a few of the things that we had to deal with. One, the side segments as defined as a period of time shrunk while we were going. Like I said, that 12 seconds shorter duration in every orbit. And so we actually built observational sequences. These are the commanding that we put up on board the spacecraft in order to operate the instruments. We actually designed some of those so that as the orbit shrunk, the sequence itself could recognize that the sequence was getting shorter, and as it went, it would cut out images. It would just self-shorten as it went, and so you could continue taking observations without constantly having to update the commanding in order to be able to handle that shorter side segments there. We had to do quite a few ongoing adjustments to the pointing and the timing of a lot of these. Some of our instruments are interested in changing what measurements they're taking depending on altitude, which you can see as the orbit changes, your altitude timing changes for all of those. And so we had to make updates yearly, weekly to be able to compensate for that. Also, your views of Mars and the surrounding atmosphere change. One aspect of the side segment observations, and I tried to illustrate this here, is that the spacecraft always looks out from wherever it is in the orbit. So as you swing around that arc in the side segments, the pointing sort of changes as it goes to be always perpendicular to that. Well, as the orbit swings in, what counts as perpendicular to the orbit, that view shed changes as well. And so sometimes before, when you were looking at the edge of Mars, now you're looking right at Mars. And if you don't compensate for that, you won't get the science that you want. Also in the apoapse segment, as we got closer to Mars, Mars got bigger in our field of view. And so we had to handle aspects of the pointing from mirrors in particular to be able to continue getting that view of Mars as we went. I haven't seen it, but I believe there would be images that would make for an excellent movie of Mars steadily getting bigger and bigger and bigger in our field of view as we shrunk down the orbit. I have yet to see that. I need to ask if that's built. And periapse, we're now passing through periapse at a higher than usual density. And there are several instruments that can be damaged by that, both by the sheer friction of the increase in that, in the atmosphere drag that we came across. There is also some oxygen in the atmosphere, and if you are allowing your instrument to come into contact with that atmosphere at high temperatures and high velocities repeatedly, that oxygen can corrode parts of some of the instruments. And so a few of the instruments put themselves in a protected mode when they're at that density corridor and effectively stop taking data. Now, I will say, because this was going to take 7 weeks, almost 2 months, there were some instruments that did not want to give up that data the way they had in the past. And they went back and did a reassessment of their density susceptibility and a new risk assessment of that. And several of them decided it was worth the risk to be able to stay on and take that data. And so they did. They stayed on during the full 7 weeks at those higher densities and got data and came out of it just fine. So once we got into our new orbit, so let's see, next slide, here we go. We'll just go from our old orbit to our new orbit. Science, of course, is impacted there as well. I mentioned the side segments. They were now quite a bit shorter. So you're not going to get those high altitude corona observations that we used to. We're now at a 4,500 maximum altitude, so we're never going to reach that 6,200 kilometers that we had been. That science is gone. On the side segment, I'm sorry, the apoapse segment, we actually had to shorten that. The side segments became so short that they almost became unusable, and we decided to shrink the apoapse segment in order to give those side segments a little more time. So we shrunk that down to basically the minimum we could possibly get away with and still be able to map the entirety of Mars. So not quite a trade-off, but it's certainly something that we had to be a little more efficient with. On the periapse side, we actually had to lengthen the segment there. This cartoon does not do a very good job of showing it, but if you imagine as you shrink that orbit, the two endpoints there near the red arrows, they drop down in altitude for a given time period that periapse covered. And so we weren't reaching the 500 kilometers that we wanted to on either end of the periapse segment. And so we ended up extending it about, I think, 1 minute and 40 seconds on either end in order to make sure that the spacecraft took periapsis measurements up to a 500 kilometer altitude. There's a lot more detail that goes into all of this. I don't have time, unfortunately, to go into it, but I wanted to give you a taste of how this aerobraking and this change for relay observations affected the science that we were doing. Question?
We do have several questions.
Oh, okay.
Okay. The first two are clarifications. So at the very beginning, did a fuel burn initiate that braking at apoapsis?
For the initial orbit insertion, is that?
For the initial braking, when you started the whole process of changing the orbit?
Oh, of aerobraking, yes. So it was a very small, relatively small burn that did occur at the apoapsis point in the orbit. Yes.
Okay. And then if dragging through the periapsis slows it down more, then why did the deep dips earlier in Mars, in MAVEN's science, slow it down in its science orbits?
It did. That's a good question. Yes, absolutely. And that was something that we were willing to take in order to be able to get the science at that point. But yes, we would go through a deep dip campaign, weekly, say, and you could actually see, in our predictions and in the actual reports that came back, that the orbit did in fact shrink. Fairly small amount, but you could see it. And so usually after a deep dip, we would have to do a compensation burn in order to get us back into the 4.5-hour orbit period that we had been in. And in fact, that was one of the larger fuel uses throughout our nominal science period. We would use just little bits here and there to manage the orbit, but after a deep dip, we'd have to do what was a relatively large burn. Still fairly small, you're talking on the order of tens of grams of fuel in those instances. So.
Okay. And so another question, given the large distance between Earth and Mars, is there disruption in the communication?
That's a very good question. So it's possible. Our data rate bandwidth decreases the further we get from Mars, generally speaking. So remember, Mars and Earth in totally separate orbits. Mars moves a little faster than Earth, and so it is possible for Earth and Mars to be relatively close when we're on the same side of the sun, and it is possible to be very far away from each other when we're on opposite sides of the sun. And so that's not a disruption so much as it is that we just have to manage how much data we can get back and forth for that. Everybody basically dials down the amount of data that they produce on the instruments when we're far away, and then believe me, they ramp it up when we get close. The one disruption that does occur, as a matter of course, is a thing called conjunction. Conjunction is when
you froze, Dale. Sorry,
Mars.
can you repeat?
Yeah,
I got a
little message there. I'll go back. So conjunction is one disruption. That occurs when Earth and Mars are on opposite sides of the sun, so that the sun is in between us. Kind of hard to communicate with another planet when there's a star in the way. And we're actually coming up on one of those instances at the beginning of September. We will be out of contact with everything on Mars for about a little over 2 weeks, I think. And so all the different missions get themselves together and figure out what they can do. They take data if they can, store it, and then after we come out from behind the sun, there's a multi-day period and we will be relaying a lot during that time, where all that data gets sent back to Earth. And then we continue with nominal operations from there.
Awesome. Last question for right now. You mentioned what the limitations for the observations, but the fact that they were making observations during this whole process, during aerobraking. Are you going to have the chance to tell us anything about what they saw, what the observations indicated?
So that's fodder for several more of these, I think, is that you could talk about that sort of thing. And since I'm not a scientist, I can't talk directly about that. I can say that for the most part, the observations that they took in the side segments in yellow and in the blue in the apoaps were very much like the observations that they had been taking, modified for changes in orbit and timing and what they were actually able to reach. But for the most part, the actual science that they took stayed fairly nominal. The periaps science always changes when you go to a deep dip. Several of the instruments turn their data rates up very high. They start measuring for different molecules and atomic atoms and ions in the atmosphere. Because of course, if you're getting down to that lower level, there's a whole other population of stuff down there. The real thing that came out of it for that periaps deep dip science is that we now have 7 weeks at a go of that measurement, whereas before you get a week at a time and then maybe 6, 9, 12 months later you get another week. Here it was 7 weeks consistently all across the Martian atmosphere where measurements could be taken. And I guarantee you there are still scientists poring over that data. We just finished aerobraking a couple of months ago, and so a lot of that is still actually being looked at a very basic level.
Awesome. Thank you so much.
Sure. Sorry I can't give more detail on that, but hopefully we can do we can get some of the other scientists on and talk about there. So that's in effect where I ended with the science impacts there is sort of the end of the aerobraking discussion. There's a couple of other things I want to talk about, and that's what we're looking at doing next when it comes to relays and changes in our orbit. So we'll jump sort of back here and have our little cartoon with Curiosity talking to MAVEN and MAVEN talking to Earth. But as many of you know, especially with the original question early on in this webinar, that Curiosity is not the only ground asset there. Last year, InSight arrived, and we are doing relay operations for InSight as well. In 2021, Mars 2020, yet another large rover is going to be arriving. There is a joint mission with the Europeans that we're doing called ExoMars that we'll be getting there in 2021 as well. And this is just in the next couple of years. Since we're looking at a MAVEN lifetime of till 2033, that's 13, 14 years in which there will be 6 or 7 other windows to travel to Mars for these robots. And there will be a lot of them at Mars, all of them taking more and more data and all of them vying for time to be able to send it back to Earth. And so our relays are going to increase from here on out. When we first started doing relays back almost a year ago, even before we did this orbit change, we were on the hook for about a relay per week, not too big of a deal. Right now, we're at about a relay per day, and it is getting to the point where it is cutting into science fairly extensively. We are feeling it from a science point of view. But here in the next couple of months and going into 2020, we're going to be on the hook for 3 to 4 relays per day. And for the amount of time that each of those takes, that will eventually come to about 50% of our time being dedicated to relay operations. So relay and science are going to have to play nice because they are becoming equal shares of the reason that we're at Mars. The one thing that some of you may have noticed is I talked about periaps being low was bad for relay and good for science, but we didn't change our periaps altitude in this aerobraking procedure. So that is another thing coming up in the near future. We had our old orbit, here's our new orbit, periaps is effectively unchanged. But in 2020, I think mid-2020, we are actually going to be raising our periaps altitude from the roughly 150 kilometers that we're at now up to about 220 kilometers. You may think that isn't a whole lot in the grand scheme of things, but that altitude, I will show back this image that I showed you before, again, with the solid line being the nominal depth that we reach in our periaps, going to 220 kilometers actually raises us up above the level of the exobase. And so MAVEN will no longer be skimming down into the true upper atmosphere of Mars. That will be a big loss for MAVEN science. It will be a big gain for MAVEN Relay, because now we will be able to predict our orbit with a very high degree of accuracy a month plus in advance. And so relays will be able to be better scheduled and better communicated all across the different assets that are on the ground. And that is pretty much it. That went a little faster than I expected, even with the questions, but that just gives us more time for me to answer questions for everybody else.
Dale, I had one follow-up question for you based on your response to the last question, and that is, so you had this effectively a 7-week deep dip, and you mentioned a risk of having corrosion to your instruments by encountering oxygen in the atmosphere. Was there any study done to predict how much of that effect you would see during this deep dip campaign that basically was similar to all of the total of the deep dip that we had experienced prior during the mission?
Yeah, that's right. We had done 9 deep dips before that, each one close to a week in duration. And so this was effectively a doubling of our time at that mid-level atmosphere. There have been many studies done about what the effects of the oxygen would be on the instruments. Some of those tests done before we even launched to get an idea of how well we would stand up to the level of oxygen in the Martian atmosphere. A lot of that has been refined since we got there. And the problem being, of course, is that we don't have a good way to test the instruments once they get to Mars. And so what we have to look at is calibration data. We have calibration data that was taken on the ground here on Earth before we launched. We have it soon after we launched, and we have it when we got to Mars. And we continue taking that calibration data because that's comparing apples to apples to apples over a long period of time. And generally speaking, when the different instruments that are susceptible to oxygen in this way compare their calibration measurements, they see a negligible level of degradation within the within the margin of error, and within what they would expect the degradation of the instruments to be after 5 years in orbit around Mars.
Thanks. We've got a couple more questions here. So can any science observations be done during relay functions?
That's a very good question, and something that we're digging into as well as we can. There are a few instruments that are what you would call orientation agnostic. They don't really care where the spacecraft is pointed. They can take their measurements wherever and under whatever circumstances. For those that do require special pointing, there's nothing really stopping them from being able to take observations other than the fact that they may not be pointed at anything interesting. One of the instruments that I work closely with, called IUVS, also called remote sensing, is very interested. They're almost always wanting to point at Mars or through the atmosphere. But a lot of time for relay, that just isn't possible. But we've been working in a way where we can actually run observations during the relays when, for the most part, instrument observations such as this would be precluded. We've worked ways that we can take observations. They're pretty low science return, but you're actually getting some imaging back that is somewhat useful. At least it's time that we've sort of reclaimed. The hope is that as we get better with relay and more of them start showing up, that we can refine those observations and make them a little more useful.
Cool. Excellent. So Francis has a question. I'm going to try to paraphrase it a little bit because I had to run it through my head a few times to figure out if I understood it. So would it be possible, do you think, would it be useful to add another mission as a relay in an orbit 90 degrees out of phase with Mars? So 90 degrees off to the side from Earth and Mars to eliminate that blockage during conjunction. So that way the Earth could still communicate with the missions at Mars during conjunction. Something 90 degrees away at Mars's orbit, but 90 degrees away.
Right. I see what you're getting at with that question. Something like that could be done. There's several reasons that no one would ever do it. One of them is that we're talking about great distances that this data has to travel over. And in fact, if you imagine the triangle that you would form between Earth, Mars, and then this 90-degree offset satellite, that's like communicating from here to Venus to Mars, or from here to even to Jupiter and Mars. Those distances can become extremely large, and so the data that you would be moving would be fairly slow for the return that you would get. Most missions to Mars, in fact, I'd say all missions to Mars, think about what they're going to do during conjunction. And they dial back their science a good bit. They simplify it quite a bit, but they do still take science during that period. They just manage it so that when they come back out from behind the sun, so to speak, that they can communicate it all back to Earth fairly quickly. The biggest reason that we or anybody else probably would never do something like that is cost. The cost for something like that would be roughly about the same cost as MAVEN. A lot of it is fuel, it's launch vehicle, it's just building a satellite with enough technology in it to be able to be a good relay and to gain the power that you have there and to stay in the orbit that it needs to be in. And those missions are in the hundreds of millions of dollars. And I don't know that anybody would think that the return on that investment was worth that, because if you're going to launch a big vehicle like that into space, scientists are going to want to stick science instruments on it and send it somewhere, not just have it as a communication relay, offset from the sun. Now, if there were ever a situation where we sent something to a planet or somewhere and the communications were going to be cut off a lot, it is a possibility that they would send sort of dedicated communication satellites. This has been talked about by NASA for years in the case of Mars, is to actually put some smallish dedicated communication satellites in orbit. If anybody followed the InSight landing, you'll know that there were actually two little CubeSats called, I think, Marco 1 and Marco 2. And they were dedicated, small, a couple times of bread box size, dedicated communication satellites. And they were technology testers. But while InSight was landing, it was sending data up to these two little satellites. They didn't go into orbit around Mars. They were just flybys. They don't have the fuel to slow down at Mars, so they just flew by. But they took that data and sent it back to Earth, and it was a test to see if it is worth having these little dedicated communication satellites at Mars. But putting one out into the solar system like that is a whole other can of worms.
Thank you. Awesome. So different confirmation of something that you said. So the different instruments function according to where MAVEN is in its orbit?
Yes, and actually I might, let's see, I might go back a little bit here if I can do this. It might take a little while. I have a lot of animations in here. Let's see. One thing that I left out, I was a little worried about time, but we have it. So this is taking longer than I expected. I apologize. Let's see, right here. And let's see if I can get this to work. This is actually a little video. I might have to change how I'm sharing my screen. Let's see. Here we go. So hopefully everybody can see this video now.
Yes, we can. Thank you.
This is a little mock-up video that shows how MAVEN's orientation changes as it orbits Mars. There in the top left, you can see MAVEN as it moves, and then the larger picture there is representation. And so this is a changeover to our periaps orientation. You can see Mars flying by there. The little sort of shaded out areas are the instruments that are on the articulated payload platform. It hangs off the bottom. They have separate pointing from the spacecraft because we want to point in multiple directions at different times. And so you can see how those change. The orientation of MAVEN changes with the orbit. That line that goes all the way across, and you can see sort of stutter stepping there is the line of the orbit. And you can see the shaded areas of the views of the different instruments, and you can see how those change as well. And in fact, not only do we do different orientations for these different sections in the orbit, we actually swap back and forth orientation, they're called scenarios, between even orbits and odd orbits. Because as it turns out, we have so many instruments on MAVEN that are vying for different times that not only we do it orbit section by orbit section, we also do it orbit by orbit in order to give all the different instruments their fair share of observation times so that they can see what it is they're interested in seeing.
Perfect. Actually, well, it doesn't matter if it was that one or your PowerPoint. In it, you had the different colors of the orbit, and the next question asked, what does the purple segment of the orbit indicate?
Okay, good question. Let's see. So hopefully I have, can you see that image again there? Good. So the purple section right here, and you'll also notice there's these green sections in here. I'll talk about those too. That purple section is actually what's called a desaturation period in the orbit. One of the other aspects, and I wasn't going to get into this, but it's a very good question. One of the other aspects of moving through the atmosphere during periapsis is that we want the spacecraft to be held absolutely steady. And so we use these things called reaction wheels that can vary their rotation rates based on electrical input. And those rotation rates act as gyroscopes. And through a whole bunch of very fancy programming, those will actually hold the spacecraft steady even as it's being buffered about by traveling through the atmosphere. The problem becomes is that those wheels spin faster and faster and faster in order to do that. And so after we come out of a periaps, we have this period set aside so that if we need it, if the wheels have spun up to very high speeds, we will use the thrusters on the spacecraft in order to decelerate those wheels. So if you imagine, if you try to rotate the spacecraft and the wheels try to compensate, you can actually rotate it the other direction and they'll slow down. So that's, we call it a desat period in the orbit. The green portions you may have seen in this video, these are called slew sections. These are 10-minute sections dedicated to allowing the spacecraft to go from one orientation to another. And so that's sort of the transition period between the different science sections in the orbit there.
Awesome. Thank you. Let's see, there was a question about cubes that Tom answered. How about how many instruments are there on MAVEN? Oh, and Tom just answered that one as well.
Oh, okay.
There's 10.
Good.
So, and he's provided links. Folks, we're almost out of time. Tom, do you want to call it at this point?
I think if there are no more questions, I did provide a few links here regarding the Marco CubeSats. As Dale mentioned, those were more of a technology demonstration, so we're no longer, excuse me, we're no longer receiving any communications from them. They did their job and did it well, and I don't know where they are now. They're sailing on past, maybe somewhere around the orbit of Mars in heliocentric orbit.
They're out there with the Tesla by now.
Yeah, that's right. They're in the glove box of Elon Musk's Tesla. And then I put a link in too at the beginning where all of our webinars are archived on this webinar page on the MAVEN website, and this talk as well will be located there in short order. And Dale, again, thanks for being here. This was very interesting, a different perspective, get the operations perspective on MAVEN and at this interesting time during the mission, so we appreciate you taking the time to be here. And just like NASA does, you've set us up for the next round of funding, like they do. You've set us up for the next round of science talks by leaving some questions open about the science that we'll find from this Aerobraking campaign, and I think we'll have to schedule one of those in the near future.
That'd be great.
So you're getting lots of kudos in the comments, lots of thank yous. And one person says their 4-year-old wants to know if you are a go into spaceman. I don't know if they mean going to Mars or just into space in general, or
general,
if you need your space sometimes.
I am a go into space guy. So Tom mentioned that I worked on Spirit and Opportunity back in the day. And one of the things that really stuck with me was the discussion. We were talking about how great the science they were doing and all the stuff that they were doing and the years that they had been driving around on Mars. And one of the lead scientists, who's a geologist, said, yeah, it's interesting. If a human being was there, we could do this in a week. And we had been there with those rovers for years at that point. People would just be better. We have better brains than we can put into robots at this point. And while I'm very happy that we have robots to be our scientific ambassadors into the solar system, I think that if we really want to get out there and really feel the stuff that we're learning, it's going to take us going there ourselves.
Awesome. Thank you so much. We all really appreciate it. And I hope that everyone will join us in September for a talk about the methane being studied in Mars's atmosphere.
Yes, that'll be very interesting.
Yeah, we'll have the MAVEN, the lead of the MAVEN NGIMS instrument, which is the neutral gas and ion mass spectrometer, Paul Mahaffey, will be presenting on some of these recent methane detections from the Curiosity rover, because he's also a scientist on the SAM instrument, which is responsible for those observations.
Thank you again so much, Dale. We really appreciate it, and everyone has commented how much they really enjoy your responses, especially your Go Into Spaceman response.
Thank you, everyone, for dialing in. I hope it was enjoyable and educational, and thank you all very much for listening.